Welcome, everybody, to Weekly Quantum World Detangled, Season 5, Episode 7. I am joined by Denise Ruffner and Atom Computing.
Hi, everyone. Denise Ruffner coming to you today from London, where it actually didn't rain today, so it's a very good day, and really excited to be here with our special guest.
And I think our special guest is sitting in the snow. Please introduce yourself and where you are calling from.
Hello, Carl Williams, basically just outside Washington, D.C., in Potomac, Maryland. Recently retired from the U.S. government and now have set up a consulting company, CJW Quantum Consulting.
And we can't wait to hear all about that. Before we get there in a few minutes with Denise, let's get to know you a little bit, Carl. And you started at my alma mater, University of Chicago, in theoretical physical chemistry. I think you had a little stint at Northwestern, but we'll forgive you for that and won't mention that here. What is theoretical physical chemistry? How did you pick that? And what was your journey those 20 years before? How did you get interested in that type of field?
So, I had a bachelor's degree from Rice University in physics and in chemical physics, and really wanted to explore and study atomic molecular physics. And, where you did this was in those days, largely in physical chemistry. So there was also people at Chicago, like Ugo Fano in atomic physics and all. So, this is what the structure I took. That led to code collisions. Code collisions, of course, touches on at least one of the approaches to quantum computing. And so, my basic research background is in very low temperature atomic physics. This is where most of the papers are. There are other things you can find out there that have to do with redefinition of the metric system, other things I did along my career path. But mostly, I would say my contributions were in low temperature atomic physics from a basic research standpoint.
So were you one of these 10-year-old boys that was already taking stuff apart, trying to put it back together, stealing books from maybe the family library about physics and chemistry? How did this get started?
So, I always had an interest in the science and playing with chemicals and taking things apart. I just have to admit that, I think I realized as an undergraduate that, my strength was what I could build an electronic circuit. I could align a laser. I wasn't good at it. If you wanted to know how the laser worked, there I shined. You wanted to make the laser laze. Well, okay, Carl could do it. It wasn't going to be quick and it wasn't going to be easy. So, I ended up on the theoretical side, but yet most of my career was working with experimentalists. I mean, if you'll see, half the papers I wrote were co-written with experimental groups. I believe that's where the rubber meets the road. And of course, Denise may have a few comments on that.
And you stuck to research out of Chicago for a little bit that very quickly ended up in government, first at the Institute for Defense Analysis. That was your first job outside academia. How did you get into government work? Is that something you had planned or just coincidence of the field you were in?
So, I basically did a couple postdocs and then freelance for actually, for 5-6 years, working off soft money, again, out of the University of Chicago largely, but spent a lot of that time at NIST, the National Institute of Standards and Technology. I got to know the NIST people very well, wrote papers with both the theorists and experimentalists there working in cold atoms. And in 1997, I decided I was tired of chasing money and living off of soft money and took a job at the Institute of Advanced Analysis, which was actually, it changed my perspective. What did I get there? I remember on one of the projects I worked on, a retired two-star admiral told me, he says, it doesn't matter if you have a technical solution to the problem. If it kills you, you're dead all the same. So, you learn that the world is more complicated than just physics. That, you have to understand the operational situation, the economic, the political, and other things. And so, that kind of opened my eyes. And after spending a year at IDA, I went to NIST and again, back to basic research. But within 5 or 6 years, I was in management, leading NIST coordinating NIST Quantum Information Program, which started in the year 2000, and became involved in U.S. government policy, other things. I think, part of that breakthrough came from the fact that IDA opened my eyes to a bigger world and a more complex thing. By the time I went to IDA, I turned down a couple of academic jobs because after I graduated from college, I really wanted to be a professor. And I soon realized that professors mostly go out and write grants so they can raise money to do research. And so I took a different path and had a great career working in this.
And I'll leave it up to Denise to find out more about your current engagements, but you left NIST about 6 months ago and are chasing money again, or why consulting?
So I actually retired officially from the U.S. government at the end of December. But I had, prior to that, set up a consulting company and began having some minor conversations on the side with potential clients. Why? We knew back in 2010 that sometime in the next 5 to 10 years, the quantum ecosystem was going to become a little more complex, that industry is going to begin engaging other things. And this all happened, I would say, around 2014, 15, when the startups started happening. And, you look out and you see that ecosystem and you realize, rarely are you in a position to watch a whole new industry develop. And I've done so much in getting the government in a position to where they can take part of that. I was very active from NIST in helping set up the Quantum Economic Development Consortium, other things in part because we'd had meetings with industry and everything else. And part of my decision to retire was to be able to go and play as that ecosystem further evolves with all the complexities associated with it, from setting up supply chains to export control to policies around technology development to all the other complex things that exist. And for me, I want to see the system turn into a multi-billion and then eventually $1 trillion ecosystem. And I felt I could do that best as a consultant. So that's where I'm at.
Few people have done more in U.S. government than you to position quantum tech. So let's learn more about your ambitions in the private sector. Denise?
Thanks, André, and everyone. I was so excited to meet Carl that I wrote my questions down, so I may read a little bit, but it's purely out of excitement and wanting to ask the right questions. And what impressed me is that really you're probably one of the most senior members of the quantum technology community. And you served in the government for decades. And I'd love to hear your perspective on where the US currently ranks in the world in quantum computing or quantum different fields. And how do we maintain leadership in some of these areas?
So I think that's a very complicated question and full of all kinds of landmines if you want to know my perspective. But, I think it depends on how you measure where we are. If you measure it by publications, I think the United States continues to be one of the largest publishers in the quantum computing field. Whereas if you look at quantum communications, China has outshined us now for a number of years. But papers are papers, and you can look at the ecosystem and everything else, and to do startups, you can look at a number of startups here that are basically came from people who came out of the UK or Australia. They come here because the US venture capital ecosystem is different. Having said this, look, if you will look at what's going on with Quantum Delta and what the Dutch government has done about setting up Quantum Delta and making this big bet, I think they're making tremendous progress. So I think it's probably less relevant to who's ahead at the moment, but what does it look like when we're done? And there I'll just come back to another field that has evolved over 50, 60 years, and that's the semiconductor industry. There will be parts of this industry that are going to be spread around the globe. And so no one nation is going to win. If you think about lasers today, and again, the atom quantum computing companies and the ion quantum computing companies, lasers are everything, and quantum communications, lasers are important again. And if you look at that market, you want a certain color laser, a certain frequency, and a certain capability, you go to country X or country Y. It's not one country; it's already multiple countries. So, I think I think if we're realistic and we look at the whole supply chain and everything else, it will be just like the semiconductor industry. It will be global. And, I can almost guarantee you, to the extent that lithography is important, ASML will still be sitting there. And all. So I think countries want to compete in part because they want a piece of the ecosystem.
Well, I appreciate your comments. I wasn't laying a landmine, but I also appreciate your comments about Quantum Delta. I was just in the Netherlands earlier this week and was really impressed by the program they've put together. I think it's a great model. My next question is kind of many pop science articles paint the picture that a quantum computer is going to solve just about anything. And we know this isn't really true. And I wanted to hear what you foresee in a 5 to 10 year time frame that a quantum computer will deliver.
Oh, again, another hard question. I expect over the next 5 years, you will increasingly see what people call quantum advantage around primarily simulation type problems within physics. And to say simulations, they may be computational and digital computational in nature, but they'll be attempting to simulate another physical system. Why? I think this is where the first payouts are. And having said that, you learn so much from both getting the technology to the point where you can do those kind of simulations, but also developing the technology so you can go on to something that is error correctable and more general. In 10 years, I'm not a visionary in any regard. I would say I expect that there will be multiple displacements in the industry within 10 years. Now, you asked me, where's the displacement? I'm not going to speculate. Why? I think you can read a lot of things. Oh, we're going to do this. We're going to do that. I think none of us really know the answer to that. But I do expect a displacement will have occurred. Do I think that we will have gotten to the end point in 10 years? And there I would say, no, it's probably more like a 20-year hike to that end point. But what you will see by 10 years is that displacements have occurred probably on the nature of $1 billion, and that the market will be evolving very rapidly and exploding.
Interesting. Thank you for that. My next question is around the government. And what role do you think the government should play going forward to make this technology successful?
So I think governments have a number of roles, and now I'm going to talk about governments in general. So again, I think when you look around the world, you can go in and look at what the UK is doing, which is a great program. You can go look at France's new program and effort in this area. You can go to Japan, everything else. I think there are a number of roles of the government. One, they need to be careful not to get to the point of picking winners and losers. But they also have a responsibility to literally look at the broader supply chain, because I think the commercial side the system integrators will come and evolve. But the problem for the supply chains is especially in something that's technology specific and technology depth, is that it's very expensive to drive the cost of a laser in a certain market down, to build the cryogenic systems that are going to be needed to be built at scale, and yet we don't know what the pull is and the push is. So the government needs to be help nurture that broader supply chain ecosystem, and there will be winners and losers in this. But what every company wants is that they don't have to rely on one supplier, but they have 2 or 3 that they can go to. And I think materials is an area that is underfunded. And I'm not going to, there's this, what I will call materials for quantum and quantum materials. I mean, looking at new quantum materials, like the NV centers and diamond and other things, I think this is really interesting. It's not clear that some of these will come along in a time to have real impact. But materials for quantum, that is, how do I produce the high quality superconducting materials I need that don't have all these oxides and oxygen centers and things that cause noise and degrade my qubits? How do I build better ion traps so that I don't have the noise coming from the electrodes and the other things? I think there are a lot of problems there that governments can help incentivize R&D in, to ensure that the basic foundational research necessary to drive the commercial markets is being done. So don't focus just on the and, focus on creating the solid infrastructure that's going to support that and.
Great answer. I think it leads into my next question on what you feel some risks are in the space. There's obviously some very aggressive roadmaps. There is a need for more tools and materials, as you said. Do you think that currently the industry is setting clear expectations for the technology and the timing? Is there overpromising? What's your view?
So I think this is a very complicated answer as well, because if you are a startup and you don't hype each of your little successes, you can't keep the engagement you need with the venture community. And yet at the same time, overpromising when you know that the path to real profitability is out there is really hard. I look, building a general purpose quantum computer is a really, really difficult challenge, and it's not going to happen tomorrow. And while the companies may begin to bring in some revenue, they aren't going to be covering their costs for some time. And I don't want to I want the market to evolve. I think it's essential to do so. we risk overpromising all the time. I have other little things that bother me. I hate the words quantum internet. This is a horrible, horrible misnomer, because the quantum internet is not going to be anything like the classical internet. It's just not. I like the word quantum networks, yes, but tell me what the real value of a quantum network is. Is the real value of a quantum network that I can network a bunch of sensors together and get a better resolution or more sensitivity? Is the real benefit secure communications? Is it communicating between components of a bigger quantum computer that are in different buildings, rooms, or perhaps halfway around the world? Tell me what the benefit is, because I know there are a lot of papers out there that talk about the things you can do, but the overhead, the classical overhead for doing this is really large and everything else. So I think the last thing I will say is, we haven't said anything about quantum sensors. And if you ask me where is the first billion-dollar market, it's in the quantum sensor arena. Whether this is better clocks for navigation and timing and cyber resiliency, or whether this is magnetoencephalography systems, because there are a couple of companies out there now that have demonstrated quantum encephalography systems that literally will change that whole industry, because again, one of the benefits of that type of technology is to study epilepsy. And the fact is, people who have epilepsy don't like to be in a confined space, and yet the existing MEG systems confine them. So I think there are going to be displacements in smaller industrial sectors. Yes, it may not end up growing to be as big as the quantum computing market, but the first application of the transistor was not a smartphone. I can guarantee you it wasn't a smartphone. The first application was, from what I understand, was to get rid of that big old ear horn so you could actually have an amplifier so people hard of hearing could hear.
It's interesting that you put quantum sensing ahead of cybersecurity. And I was wondering if you could say a little bit more about the prospects for quantum cybersecurity.
Oh, so everybody knows, and quantum cybersecurity involves a couple of different things, new ways of getting random bits. But most even pseudo-random number generators are pretty damn good, and as long as you haven't done something foolish, they work. If you want to talk about replacing public key infrastructure, especially the asymmetric components, the things that provide authentication and digital signatures, well, this is absolutely essential, because the quantum computer is going to take this away. But having said that, post-quantum crypto, or what we call quantum resistant cryptography, is really just another classical algorithm that doesn't have more than a square root capability on a quantum computer, a hard search capability. And I think the whole world has to be prepared for this. I mean, everybody needs to be working on knowing what all their crypto is, and being sure that once the algorithms are approved and standardized and everything else, that we're in the race to replace our current cryptography. Having said this, I was just on a conversation with a cyber expert just the other day, and as I pointed out, probably the biggest risk that will be left behind is IoT. Why? A lot of IoT devices have the cryptography built into them. It's not upgradable. And anybody who understands the cyber domain understands, your weakest link is the weakest point of failure. And there's going to be a lot of legacy points of failure lying around when we're done. So I hope that answered the question. Maybe there's a second part to it.
That answers the question, and I'm cognizant of the time, so I'm going to hand it back over to you, André. But thank you. I really appreciate your answers, your thoughtful answers.
And very thoughtful questions. Thank you, Denise. Carl, I have two questions for you about fault-tolerant quantum computing. The second one is part of our little quiz, but the first one is a question somebody asked me a few weeks ago, and I'd be very curious to hear your answer. If you had a fault-tolerant quantum computer, why would you even tell somebody?
So, I believe the real value of this technology is what it contributes to the broader community, and it will redo perhaps how we do drug design and other things. So if you don't tell anybody, you have nobody using it. I think I know there's a lot about nation state actors kind of things and everything else. Look, commerce and the economy is a far bigger thing than breaking codes, and yet the codes will create risks for a large number of people. So I truly think that when we're done, once it's the real value of semiconductors, is it the consumer piece of the enterprise? Is it program trading? Is it the fact that Boeing can design a plane, or Airbus can design a plane on a computer, go build it, and it flies? So tell me, the real value, I think, is economic, and it's going to be both commercial and maybe one day in the far, far future, consumer. But I wouldn't hide it, because it is all about the economy.
May you be right. Let's wrap up with our infamous Marcel Bruce, James Lipton quantum questionnaire. Carl, 6 rapid fire questions, and your mission, shall you accept, is to give rapid fire, one word, one sentence kind of answers. So whenever you're ready, let's get started.
Oh, now I'm sweating.
Let's bring your heartbeat down and get started. Who is your favorite scientist, Carl?
Richard Feynman.
Do you have a favorite entrepreneur?
No, I'm learning from all of them.
What is the quality that you desire most in a scientist?
Curiosity and intellectual integrity.
What do you appreciate most about working in quantum technologies?
At the moment, the very diverse ecosystem there is, from venture capitalists to technologists to C-suite executives.
What is your favorite quantum tech application at a personal, intellectual level?
Relativistic geodesy.
Which is?
I like giving this one because this goes back to a network of sensors that could perhaps look at the fundamental modes of the Earth, but also detect earthquakes before they happen, or volcanoes before they blow up.
I just visited a volcano. It was fuming but not blowing up, so we have some time to bring that to market. Do you have a quantum dream?
Yes, to see the technology truly displace and change the world.
A quantum nightmare?
No.
You're very optimistic for having worked in government for so long. That's reassuring. Back to fault tolerant and our last question. Imagine you wake up tomorrow to the first ever fault tolerant quantum computer sitting in your living room. The only one in the world. You're not allowed to use it. Who do you give it to?
Wow. Now I'm speechless. Who do I give it to? A pharmaceutical company.
Interesting, and very relevant to our time still. Carl, it was an absolute pleasure having you on Weekly Quantum World Detangled. You are now in consulting for the last 6 months. I know you have a handful of clients already, CJW Consulting. You'll be hard-pressed to find somebody more knowledgeable and better connected in quantum than Carl. Thank you, Denise Ruffner. Thank you, Atom Computing. This concludes the Weekly Quantum World Detangled, Season 5, Episode 7, and you are now detangled.